So in the previous class we have an introduction to schedules. So what do you mean by schedule, and other things were discussed. So schedule is actually, if we are given with a set of transaction, what way we will execute that set of transaction in an interleaved fashion. So that is actually scheduling of the transaction mean. So in that case, we view different types of conflict that can occur while we schedule different transaction. Then conflict means if we schedule transaction different order, it can result in the final result can change. So that is actually conflicting meant to be. So next we are going to study how we can schedule. There are two ways in which we can schedule. One is based on recoverability and second one is based on serializability. So in today's class we are going to study both of this. So in this case the most important one is actually serializability. So most of the questions are came from that part, but recoverability also an important one. You may get problems from serializability portion. So schedules based on recoverability are mainly classified into three. The first one is a recoverable schedule versus non-recoverable schedule. So and second one is cascading schedule and cascadeless, and last one is strict schedule and non-strict schedule. So recoverability schedule are always checks whether the schedules are arranged in a manner that after a crash all the transactions which are committed should be recoverable. Okay, so that way we have to arrange the transaction in the schedule. The schedules that meet durability property are called recoverable schedule. So that thing I said, after the crashing all the committed transaction has to be redo. Okay, so successfully it can be redone. We will see what all are non-recoverable schedule. So the definition of recoverable schedule is as follows, or how we can what is the rule or what is the principle behind the recoverable schedule, or what way we can make a transaction into a recoverable schedule only by following these principle. The principles are actually first one is the most important principle. The definition of a recoverable schedule is as follows: a schedule S is recoverable if no transaction T in S commits until all transaction T dash that have written some item X that T reads have committed. So that it indicates that. But suppose you have a particular transaction TA which reads some data item which is already updated by other transaction like TB or TC, or some other transaction are already updated. Then next one, TA read after they updated the value, and the principle says that TA can commit only after the other transaction like TB, TC, TD committed. Only after they committed TA can commit. So it's actually this schedule is doing or it is actually avoiding try to avoid the dirty update. So you just go and check what do you make dirty update. So if particular transaction read some value which is written by other transaction, then that transaction can exit only if first transaction, that means that transactions return some item some or updated that element. Okay, only after they committed this particular transaction can commit. So that way you have to schedule. Then if you schedule in that manner, then it can be easily recoverable, or after a crash the database system can easily recover or easily redo the same operations that the transactions done before the crash. A transaction T reads from, that's the second principle, transaction T reads from transaction T dash in a schedule as if some item X is first written by T dash and later read by T. So a particular transaction I need to check into only one of the other transaction. That means a transaction, suppose a transaction T read a data item X, and before transaction T reads that data item, TA, TB and TC already wrote something or already updated the value, but the T need to be compared or checked only with TC. TC is the last transaction updated the data item X before the transaction T read the data item. So we need to compare only that two transaction. We no need to go and check with the TA and TB. The last transaction TC is actually updated the value, so we need to cross verify only the last transaction TC and the transaction T which reads the data item. So that is the second point says. In addition, T dash should not have been aborted before T reads item X, and there should not be no transaction that write X after T dash write it. So write it and before T reads it. That means there should not be any other transaction in between that those transactions that I have already said. TA, TB, TC written as some element. We need to check only TC and T. Not need to check TB and T, because in between TB and TC also wrote something into that X. So we need to compare only the last transaction that's updated the data item and the transaction which reads the data item. And the other point is T dash should not have been aborted before T. That is, before T reads the item, then but before that TC aborted, then there is no problem. Okay, so then these are the three principle. If we are following, then you have to meet recoverable schedule. So let's move to some example. Here you can see first three transactions, SA dash, SD and SC dash. These three transactions are some examples of recoverable, and last one is an example of non-recoverable schedule. Okay, so we can first move into non-recoverable schedule, SC. So the schedule SC, if you schedule in this manner, go and check whether it meet the principle. So firstly you need to check the first principle. That means a particular transaction read the data item, so write the data item, and following other transaction read that item. Then the followed item or the later item can commit only the first transaction commit. So here you can see in the non-recoverable schedule, here you can see R1 of X first thing that schedule. So that indicates the transaction 1 read the data item X. So no need to worry about it. But in second case, the particular transaction write the data item. So the transaction 1 write into data item X. Now we need to check whether any other transaction reading those data item. Okay, so in the third command or third operation is transaction T2 read X. So that indicates transaction T1 wrote something on X, and after that transaction T2 read the item. So the principle says that only the transaction T2 can exit or abort or commit. It can commit only, not abort. It can commit only after transaction T1 committed. So here you can see the thing is here a particular data item is written by transaction T1 and following or is after that, not the just operation. It is can be R2 of X can be at the last operation, can be the last operation. So here you can see it is just following right item. So transaction T1 return something into X, and then transaction T2 read that data item. So the principle says that first transaction T1 has to commit or abort, and by when we check when we check the schedule, you can see that firstly transaction C2 committed, and after that you can see transaction T1 committed. So what is the problem? Why this is a problem? Because we are scheduling based on recoverability. So suppose after this schedule, after completing all this operation and doing some other operation, there is a crash in the system. Okay, some crash happened in the inside the system, and due to that crash, the system goes to restart stating, and after that DBMS restarted, it first go and check the what thing, the system log. The system log says that the transaction T1 started and ended as abort. Okay, okay. So and after that you can see transaction T2 but actually started and committed. That indicates recover case. In the recoverability we are going to do undo operation on transaction T1 because it is actually aborted. Okay, and we are going to do redo operation on T2 because it is committed. So what will happen, the transaction T1 firstly do all the things back, and suppose it is not undoing anything, the because already aborted, the transaction is already rollback. So what will happen is that when we try to redo transaction T2, it will actually require a value returned by transaction T1, but while it is aborted, that particular transaction is aborted, here you can see while it recover from the crash, it is not getting the correct value. Here transaction T2 needs a value which is updated by W1x transaction T1, but at the case of redoing operation, we after recover from the transaction, we won't do any operation, or we won't redo any operations of T1. That is, this W1 of x is not executing, but you can see R2 of x must execute. Okay, because it's durable, satisfy durability property. So but R2 of x is getting the old value. Okay, so this is actually dirty read actually showing. So in the university questions you may be given things like this. Okay, and you have to say whether it is recoverable schedule or non-recoverable schedule. Okay, sorry. So in that case you have to check whether the committing is in the correct order. So now we can check the recoverable schedules. So here you can see R1 of x, that's not can create any problem. We need to check the write operation first. So here you can see transaction T1 wrote something into, written something into x. So what then we need to check whether any read operation is going to be happened in any other transaction. And here you can see nobody is currently reading, only two transactions are currently in this schedule, and the T2 is not reading the value, it is just writing the value. So T2 is not reading the value of x, it is just writing. So we not need to think about it, we need to check whether write is followed by read, and then so it's not a problem. But here is again a write, so we need to check whether here W2x is followed by T1x, oh sorry, R1x, that is after the W2x whether the transaction T1 read x. Okay, but it is not also given in this statement. And so then you can see already write in y, and or after that there is no write, read to y. So we can check there is no operations that follows the first principle, so anyone can commit. So here you can see the first transaction C2 is committing and followed by transaction C1 is committing, so it is a recoverable schedule. So first we need to check whether the first rule is satisfying in any of your scheduling, and if it is satisfying the schedule, then you have to follow the order of commitment. In the second case, so here you can see in the second SD R1 of x, no, it's a problem. So then you can see W1 of x. Now you have to check whether any other transaction read x. You can see transaction T2. Transaction T2 is actually reading the data item. So the principle says that T1 must end first, and only after that T2 must end. And then followed by R1y, it is not getting any problem. Then you can see W2fx, W1 of y, and here you can see C1 firstly committed followed by C2. So this is also a recoverable schedule. So some may be in doubt that whether C1 followed by C2 or C2 followed by C1. It's actually a non-recoverable schedule. If the operation is like that, then we need to check um, whether I have a cycle or some other things. So we will look into those things in our later slides. So it does not have any cycle. That means the operation must not be like that. So here you can see it is a non-recoverable, sorry, recoverable schedule. And third case also you can see both the things are aborted. Okay, and so it's also a non-recoverable schedule. And in the aborting case also, here you can see A1 followed by A2. So W1 of X followed by R2 of X, and then the abort also should be like that. First you have, if transaction A1 aborted, then transaction A2 must abort. Okay, so that is the case. Transaction A1 aborted, then transaction A2 must aborted. But there is no case like that. Transaction A1 committed, but transaction A2 can abort. So it's not a problem for transaction A1, sorry, transaction T1. If transaction T1 committed and followed by transaction T2 aborted, it won't affect transaction T1. Okay, so that's also a problem. A C1 colon A2. It's also, it is also a non-recoverable schedule, because transaction T1 is not dependent on T2. Okay, so C1 can commit and followed by A2 can, that means transaction T2 can abort. That is actually, but the opposite, if transaction T1 aborted, then must transaction T2 also aborted. That is actually cascading schedule. So that is actually cascade schedule. In a non-recoverable schedule, no committed transaction ever needs to be rolled back, but in a non-committed transaction may roll back. So that we know that in the case, this is that case. So suppose T1 aborted, then we know that it will do a rollback on W1 of X. So it is actually creating again the dirty read. So transaction T2 is actually doing a dirty read. So if T1 aborted and T2 is actually depend on a variable written by T1, then automatically T2 must aborted. So even though transaction T2 completely do all its operation, it can be aborted if T1 failed. Okay, so that is cascading schedule. So this is actually following the cascading operation, that is A2, that T2 is aborted due to A1. So when an uncommitted transaction has to be rolled back because it read an item from transaction that failed. So that is cascading schedule. Next one is schedule based on recoverability. So it is actually a simple thing. Here you can see you are following strict or non-strict scheduling. So in a transaction can neither read nor write an item X until the transaction that wrote X has committed. So that is particular transaction read something or write something. So no other transactions are allowed to read or write that item until that transaction, the first transaction, committed. So they have to wait until that particular transaction committed. So it is also creating a recoverability. So it is not creating any problems, because the first transaction committed after writing the operation to commit, then only it going for reading or writing. So the second transaction won't be affected by the any cause or any issues inside T1, okay, or the first transaction. So that is actually strict transaction. Means if a particular transaction need to read a particular data item, first it has to check whether any other transaction currently written or something into that. If any other transaction already written something into that X, then it has to wait, the second transaction has to wait for the commitment of the first transaction or abort of the first transaction. So that is a strict schedule. The others has to wait. So it is actually creating a level 3 durability, you can say. Actually here we studied only isolation, level 1, level 0 isolation. Here you can say level 3 recoverability, okay, or durability. So next we are moving to schedules based on serializability. So this is an important thing when comparing to recoverability. Most of the DBMS are using serializability. So serializability means that uh, you know that serialized schedule or schedule which are scheduled in a serial manner is that first suppose you have 10 transaction, then you have to do the transaction in one after another way. So that is first you have to execute T1, and after completing or aborting T1 you can start only T2. Then after that you only committing and aborting T2 you can start only T3 and etc. So if we schedule in a serial way, it won't create any problem because only a particular only one transaction is allowed to execute at a time. Okay, so that is actually serial schedule. So here you can see serial schedule. So serializability of a schedule is used to identify which schedules are correct when transaction execution have interleaving of their operation schedule. But we know that if you execute all operation in a serial manner, it is to create waiting problem, no other problem, but it create long waiting time for other transaction. Suppose a particular transaction T1 is executing and it require some huge data item from a particular RAM or a hard disk, then it has to wait and all other has to wait for the commitment or abort of the first transaction. So our operating system or the DBMS software looking for fast execution of all the transactions, so they are trying to do parallelly executing the whole transaction, or we can say we need to execute the transaction in an interleaved fashion. So we can't go for a serial execution, so that we create only delay in operations. Okay. um, okay um, so here our aim is to find the serial schedules of the given transaction, and also try to find different interleaved schedules also. Then we need to check whether any interleaved schedule is matching to our any one of the serial schedule. Okay, so that is our aim. So we need to check this thing for completing or finding a good serial schedule, serial schedule having serializability. So we will check we'll study in our next slide. So here you can see two transaction T1 and T2. If the arrival time of T1 is before T2, then T1 firstly execute and after T2 execute. And if the arrival time of T2 is before T1, the T2 will firstly execute and after that T1 execute. So it's not creating any problem. Serial scheduling are not creating any problems. So you can see T1 firstly execute in the schedule A. T1 firstly completed its execution, committed or something about the transaction. Some operation happened, and only after T1 successfully aborted or successfully committed, T2 start its operation. So that is the first schedule. And second option is you can schedule first T2 and after that T1. So end result can change, but you can say the arrival time of T1 is before the arrival time of T2. So there is no problem in that case. In the serial schedule, the ordering of schedule is not a problem. Another two schedule, but it is following an interleaved fashion, schedule C and schedule D. So if interleaving of operation is allowed, there will be many possible order. Okay, so suppose there are two transaction T1 and T2, you can schedule serializability. You have only two cases for that, schedule A and schedule B, T1 after T2, T2 after T1. So that are only cases. But if we are following interleaved fashion, there are different possible options. So first transaction can be executed, the first command of first transaction, then followed by the two commands of second transaction, then followed by two command of first transaction. And it can also be changed, like first you can execute two transaction of T1, then followed by one transaction. So there are different possible interleaved fashion. So here you can see there are they're given two schedule C and schedule D. So we are more going to look into that. So before that, serial, non-serial and conflict serializable schedule. So transaction is said to be serial. The operation of each transaction are executed consecutively without any interleaved operations. So A and B are serial and C and D are non-serial. Every serial schedule is considered correct. It does not matter which transaction is executed first. The problem if a transaction waits for, so that's they are saying the problem of serial schedule, wait for an IO operation to complete. We cannot switch CPU processor to another transaction because it's scheduled in that manner. Only T1 T2 can start only if T1 completed, so thus wasting valuable CPU processing time. So if some or transaction T is quite long, that other transaction must have to wait. Suppose that there is no input output operations, but the transaction T1 contain 100 operation. So it started execution, and in the meanwhile T2 arrived, it contained only 2 operation, but it has to wait for the first transaction to be completed the 100 operations. So that's are the problem while we are executing the transaction in serial manner. Next, we are going to serializability of a schedule. So both are different, serial schedule and serializability of a schedule. So serializability means we are trying to match a non-serial schedule, or we can say an interleaved schedule, to a particular serial schedule. And if there is a match you can find, then you can say the interleaved schedule is serializable. Okay, I think you understood. So in the example C, given an erroneous result because of the lost update. So here you can see in this example we already saw this in the lost update problem. So here you can see T1 updated the value, but before updating or writing item into secondary device, the T2 read the old value. So that is creating the lost update problem. So in the before in the recoverability case we are checking the dirty read problem. Here we are actually checking the lost update problem. Okay, so schedule C gives an error because the lost update problem. T2 reads the value of X before it has changed by the transaction T, but schedule D is a non-serial schedule, give the correct result, expected result. So we can say schedule D is serializable. So we are going to look at how we can say particular schedule is serializable. But just look this example. Here you can see there is no lost update. So there is no lost update. We can say the thing is serializable. So transaction T1 completed its writing operation. Only after that T2 start to read the data item. So we lost the lost update problem. So we would like to determine which one of the non-serial schedule always give a correct result and which may give erroneous result. So this is definition of a serializable schedule. A schedule S of n contain n transaction which is said to be serializable. Okay, or not non-serializable. Okay, so serializable means something is in a non-serial manner which can be matched to a particular serial schedule, compared or which is equivalent to another serial schedule. So that is serializable. So if it is equivalent to some serial schedule of same transactions. Okay, I think you understood the thing. A non-serial schedule S is serializable is equivalent to saying, a non-serial schedule S is serializable is equivalent to saying that it is correct because it is equivalent to a serial schedule which is considered correct. So we already saw that all the serial schedules are said to be correct. Okay, so one is followed by another. So it is even though the order is changed, all the serial schedules are correct. Okay, so if you match a non-serial or an interleaved schedule to any one of the serial schedule, then we can say that non-interleaved schedule is said to be correct. So how we can find two schedules are equivalent? Whether we need to compare whether a particular interleaved schedule is equivalent to any one of the serial schedule. So we need some mechanism to identify that. So ways to identify equivalence of schedule. So there are going to say 2 3 methods. The first method is a simple method, but it is not a correct method. The simplest but least satisfied definition involves comparing the effect of the schedule on the database. So you have to run the serial schedule and followed by the non-serial schedule. Okay. So if the both are getting same result, then we can say both are same or equivalent. But there are some problems arises. Suppose you have an operation S1 and S2. Whether we can say S1 or S2 are getting same result. It will get the same result if the value of X is 100. Let's do the addition operation here. 100 is equal to, sorry, the old value of X is 100, so X is updated as 100 plus 10. So you will get the new value of X as 110. And here in S2 the operation is different. Actually you are doing another operation, so both are not equivalent. Okay, so here X is assigned as 100, so 100 into 1.1, it's also equivalent to 110, but it is not getting result for any other value. Suppose you are doing 50, so 50 plus 10 is 60, is 50 into 1.1 is 60. So it's only possible if the value of X is equal to 100. So we can't say if the schedules are getting same result for a particular data or a particular value, it won't say they are equivalent. So ways to second way, so ways to identify equivalence of schedules. So second method is, for two schedules to be equivalent, the operations applied to each data item affected by the schedule should be applied to that item in both schedule in the same order. So this is one of the important method. So it says that if you are doing some operations into a data item in a serial schedule, then you have to follow the same order in the non-serial schedule. If you can see some non-serial schedule in that manner, suppose a non-serial schedule contain different operation on data items. If you followed an order in that non-serial schedule or an interleaved schedule, and you can see that there is a serial schedule which follow that order, then you can say both are equivalent. So we can see the example here. So before going that, conflict equivalence. So after this definition, so we can go into an example. So conflict equivalence means two schedules are said to be conflict equivalent if the order of any two conflicting operation is same in both schedule. So that's another case. If we can, you have to check these two principles. The first one is you are following the same order of a serial schedule. Okay, but it is interleaved manner. The data item are the operations upon data item are in same order or of the serial schedule in the non-serial schedule. And the conflict equivalence means if there is a conflict in between two operation in a serial schedule, then it should be in non-serial schedule. Okay, so conflict also in same way in serial as well as non-serial. Then we can say that non-serial and serial are equivalent. Okay, so they are producing the same result, or we can say you can run that schedule. So if a read and write operation occur in the order R1 of X, W2 of X in schedule S1, and in the reverse order in W2 of X and R1 of X in schedule S2, value read by R1 of X can be different in two schedules, so it is not conflict equivalent. So this here you can see we are doing conflict operation. Yes, in the last classes you studied what we mean by conflict operation, what are the conditions in a conflict operation. So here R1 followed by W2 and the other schedule W2 followed by R1, so it is not conflict equivalent. That schedule is not equivalent. So equivalence between serial and non-serial schedule. A schedule is to be conflict serializable if it is equivalent to some serial schedule S. So here we are actually concluding our previous statements. So we can reorder the non-conflicting operation S until we form the equivalent serial schedule S. So that is the second statement. So first statement already concluded our things. A schedule S is conflict serializable if it is equivalent to some serial schedule. Okay, so we can say schedule is equivalent if only if it is equivalent to some other serial schedule. And second thing is that suppose you found that there is no matching between a particular interleaved schedule and any of the serial schedule, but you can do some sort of modification in the interleaved schedule, or you can say the non-serial schedule, and you are achieving an equivalent to some serial schedule, then it's also correct. But one thing is that you can't move any conflicting operation. You can move the position of serial schedule, so move the position of non-conflicting operation in the interleaved schedule. Okay, and if you achieve some matching, then you can say it is also equivalent. So here you can see some example. So according to this definition, schedule D is equivalent to schedule A. Here you can see schedule can take schedule D. Here you can see first thing is that you have to check whether all non-conflicting operation. So T1 and T2 we have to take schedule A. Schedule A is a non-serial schedule. How the conflicting operation comes in X. So here T2 read the data item, and before that T1 write the data item X. So this is the conflicting, these are the conflicting operation. So whether first, but it's given that T1 write followed by T2 read. Okay, so that is the order of the conflicting. T1 write, then followed by T2 read. So you can check in D, the non-serial schedule. Here also you can see that the conflict operation T1 actually writing and followed by T2 read. So write followed by T2 read is happening in this schedule, and no other conflicting operations are there. So you have to check all other conflicting operations. Here Y is not creating any conflicting operation, but because T1 is not accessing in Y is not accessing in T2. So we can say A and D are equivalent, but just check A and C are equivalent. Here you can see inside schedule C, okay, first read item X, it's not a creating problem, followed by T2 read item X. So they are not conflict, because we only in the condition of conflict operation there is a point is that either of the operation is should be right. So T1 read item of X and T2 read item of X are not creating any conflict. But then second operation you have to take T2 read item of X followed by write item of X. So this is creating a conflicting operation. So whether it is equivalent to A contain the conflicting operation write and read, but it is in the order T1 write followed by T2 read, but here it is T2 read followed by T1 write. So the order changed. So we can't say A is equivalent to T1. No other conflicting operations in both C and A. So whether we are going to check whether it is same as T2. Sorry, B. We have to check whether C is equivalent to B. So go and check C is equivalent to B. Here you can see T2. Sorry, inside the schedule B, the conflict operation is between whom and whom. First T2 read the data item X. There is no conflicting operation between that, and after there is an operation X equal to X plus M, and after that you can see write item of X, and it followed by read item of X. So actually the conflict is between write item of X in T2 and read item of X in T1. So that's creating the conflict. So T2 write followed by T1 read. So whether it is like that in schedule C. So it is also, we can see read item followed by write item, not write followed by read. So this the schedule C is not equivalent to B. So there is only two serial schedule for T1 and T2, either T first then T2, T1 first, T2 followed by T2. and the second serial schedule is T2 first, then followed by T1. So the C is not matching to any one of A or B, but you can see the schedule D is matching to A. So you can say that D is equivalent to A. And here you saw one more point, is that we can reorder the non-conflicting operation S. So try to reorder schedule C and try to match into either A or B. So is it possible to order? So you can see only it matches to schedule A. The C matches only to A if write in T followed by read in X, read in T2. So for that, either you have to move right item little more about to x equal to x minus n. So but it is not possible, because the thing is that only you can move non-conflicting values. So you can move read item of x, so read item of y and write item of y. Here you can see right item of y is here. You can move near to y and y plus n, and right item of y can be moved to under read item of y. Then you can write right item of x, because this right item of y or read item of y is not creating any problem. So you can easily move this thing, but don't reorder the operations in the transaction. You can't move right item of y to the first position, but you can move it to this position, to read item of y, near to read item of y, because they are not creating any conflict. But you can't move right item of x, read item of x in T2, and as well as you can't move right item of x in T2, because it is actually in conflicting operation with right item of x in T1. So you can't move this their position. Okay, conflicting operation can't move their position. So C, even though we moved the non-conflicting operation, is not making any match to either A or B. So here I am explaining the same thing. Schedule C is not equivalent to either of the two possible series schedule A and B, and hence it is not serializable. Trying to reorder the operation of C to find an equivalent serial schedule fails because R2 of x and W1 of x is conflict, which means that we cannot move R2 of x down to get equivalent serial schedule T1 or T2. So similarly, W1 of x, W2 is also creating conflict. We can't move W1 of x down to get an equivalent serial schedule T2 of t. So C can't be make into a equivalent non-serial, sorry, serial schedule. So you can do in this manner, but you know that suppose in question you are given the T1, T2, T3, T4, T5, 5 transactions are given the university question. So you can't find the way to move this all operation. So in the next class we will study how we can test whether a particular non-serial schedule can be matched into a serial schedule. There are an algorithm for finding, not we are trying to move these all three operation, but you have question may come for the university exam to find how we can do this operation. So you have to study an example for that. But there is another way, that is actually you can do testing for conflict serializability of a schedule. So we can study in our next class.